Hi everyone, my name is Karthik. Today I will present my case study that is comparative study of Lidar and camera technologies in autonomous applications. The objective of my case study is to conduct the comprehensive comparative analysis of Lidar and camera and the sensor fusion of Lidar and camera sensing technologies. My comparative analysis based on some key aspects like accuracy, cost efficiency, environmental adaptability, and data processing requirements, and the suitability of real-time applications, especially in autonomous systems. So for this comparative analysis, I have taken like 8 papers, 4 papers for the comparative analysis of LiDAR and camera technologies, 2 papers for the LiDAR technology, and 1 paper for the camera technology. Next, I will present my papers for the literature review. This is the first paper in my literature review, that is LiDAR versus camera-based perception in autonomous vehicles. It is published year 2022 in the journal International Journal of Core Engineering and Management. This paper mainly focuses on the comparative analysis of LiDAR and camera-based perception systems in the simulation in different kind of environments. It evaluates key aspects like accuracy, environment adaptability, processing latency, and cost effectiveness. The objective of this paper is to compare the LiDAR and the camera-based technologies in terms of detection accuracy, computational adaptability, computational efficiency, and system cost and robustness. The methodology they have taken in the terms of simulation environment. For that, they have taken different environmental conditions. Uh, then they have taken the data collection of the both the LiDAR and camera systems in different various environments. Uh, then they have done the pre-processing work, cleaning and processing the data from the both sensors. Then they have combined the LiDAR and camera data by side-by-side comparison. Then they have given the matrices for the both the LiDAR and camera based on the accuracy, resolution, speed, and adaptability. Um, on the analysis, they discuss about the strengths and weakness of LiDAR and sensor in different scenarios. When I talk about the limitations of both LiDAR and camera, LiDAR is having high cost, weather sensitivity, and processing burden. It is expensive to implement in real world applications. It is having weather sensitivity that drops its performance when it is in rain or snow conditions. And it need lot of data and it need lot of computation power and it need lot of time to process all this data. When I talk about the limitations of the camera, it is light dependency, environmental variability, and inconsistent in very accuracy. uh, Camera is uh, drops its accuracy when there is low light or dark and dawn scenarios, and environmental variability by changing the weather and lightning conditions, it changes its accuracy. So it is inconsistent in accuracy. When I talk about the results of this paper, is like lidar is performing good in low light conditions, and camera is cost efficient than the lidar, and it is camera is better in daylight conditions than lidar, and efficient processing than lidar, and lidar is having high spatial resolution than the camera, and it is consistent in mapping. Then when I talk about the second paper, it is comparison review of LiDAR versus camera in autonomous vehicles. It is published in the year 2022 in the International Research of Journal of Engineering and Technology. The overview of this paper is like comparison between LiDAR and the sensor camera based systems in autonomous vehicles. And in this paper they have mainly they have focused on strengths and limitations of each and individual sensor and benefits of the sensor fusion also. The ultimate goal is to enhance safety and environmental awareness in self-driving cars. The objective of this paper is to access the effectiveness of sensor fusion for the object detection. For that, first they need to use the effectiveness of LiDAR and camera systems for the autonomous driving. The method in this methodology, first they have taken the data of the LiDAR and camera and classify the objects of the camera captured data by using machine learning, and they have used the stereo and TOF camera for the depth perception and 3D mapping. The algorithms they have used is like regression, clustering, and pattern recognition for the sensor data. The data set they have used is like Kitty data set. uh, when I talk about the advantages, limitations, of the both lidar and camera as per this paper is like lidar is high depth accuracy, uh, and when I talk about the limitations, it is having expensive. Lidar is works in all light conditions, minimal human dependency, and harsh weather tolerance. But camera is low cost and power consumption, and recognize colors and signs also. And camera is mainly based for the object classifications. When I talk about the limitations of camera, it's like it is affected by the weather. We all know about that, and low depth accuracy and limited field of view. The main drawback of lidar is like it need to process the complex data, and main drawback of camera is it it accuracy is like inconsistent due to affected by the environmental conditions. The conclusion of this paper is like sensor fusion of lidar camera plus radar will be give the maximum best results than the lidar and the camera individually. So both having their weaknesses. So we need to make it as sensor fusion for the best results. This is my third paper, that is a comparative analysis of lidar, camera, and fusion-based deep neural networks of vehicle detection. It is published in year 2020 in the International Journal of Innovations in Science and Technology. The overview of this paper is like comparative study for the vehicle detections by using three different sensors, that is lidar, camera, and fusion of the both. They use the Violo V3 BEV network and point fusion on the Kitty datasets, and based on some key aspects like accuracy, collision handling, and computational complexity, they have given some conclusion. The objective of this paper is to evaluate the performance of three deep learning based object detections, um, like camera, lidar, and fusion of the both in the with respect to detection accuracy, performance, and in different environments and computational complexity. Methodology: first, they have taken the Kitty datasets with images and lidar in point clouds. They mainly focusing on detecting like cars, pedestrians, and cyclists. They trained the YOLO V3 and DNN models like YOLEX MV3D on different modulations like using Kitty dataset and compared the accuracy and the robustness. They trained the BEV model for the LiDAR data, and they trained point fusion model of the both images and LiDAR data together for the sensor fusion technology. Uh, the limitations of this paper is like for the sensor fusion using point fusion, it is having high complexity. For the lidar data using BEV model, it loses some details due to conversion of 3D to 2D data. And for the camera based detection, YOLO V3 misses some details. Um, and it is having some lag issues when we perform this evaluation in hardware. The overall conclusion of this paper is like sensor fusion is having good outperformance the camera and lidar, which is done by the YOLO V3 and BEV models. Despite of the higher computational cost, Fusion provides the most robustness accuracy than the other two models. This is my fourth paper, that is research on comparison of lidar and camera in autonomous vehicles. It is published in the year 2021. The main objective of this paper is like to compare the perception, performance, strengths, and weakness of the lidar and camera technologies in autonomous vehicles. The overview of this paper is to compare the lidar and camera technologies in autonomous vehicles for the in the environmental perception. When I talk about the objective of this paper, once again, that is to discuss the necessity and value of multi-sensor fusion for the accurate environmental perception and about the autonomous vehicle behavior. Methodology of this paper is like they have done the qualitative and quantitative comparison through the literature review and experimental focusing and environmental perception and object detection and driver safety. First, they have reviewed some papers and they have done the comparison of the lidar and camera technologies in autonomous vehicles and explained how lidar and camera works, including their features and technical differences, and analyzed the differences between both of them, and highlighted the real research examples like using stereo cameras and depth cameras, and they have done using the AI technologies like deep learning and machine learning to process the data. The limitations of this paper is like Lidar is very active but expensive for the most cars. Camera is cheaper but does not work for the all conditions. Um, for the perception view and the depth accuracies, Lidar is having some superior accuracy in 3D perception than camera. Uh, and camera provides richer semantic information fusion necessary for the robot perception. And it is hard to process both sensor fusion data, and it is having some time complexity issue. Fusion needs complex software and hardware for working together smoothly. This is my fifth paper that is only focused on Lidar. Lidar for autonomous driving, the principal challenges and trends for automotive Lidar and perception systems. It is published in year 2020 in the institute like research division, Donald H.S. France. The overview of this paper is like it represents a comprehensive review of automotive Lidar technologies in Lidar-based perception systems. As per the name, we know that it mainly focuses on principal challenges and trends for automotive Lidar in perception systems. The objective of this paper is to review and analyze the core principle behind the Lidar technologies and automotive applications to evaluate the perception algorithm used for the processing Lidar data to highlight the challenges and predict the trends in Lidar development for autonomous driving. The methodology they have used for the Lidar data is like time of flight, we all know, or frequency modulated continuous wave methods. And for the object detection, they have used filtered ground paths and clustering data to identify the objects. And for object recognition, they classify the objects using machine learning. For object tracking, they track the objects by using time with filters and data association. The conclusion of this paper is like the crucial role of Lidar data in enhancing the perception systems in autonomous vehicles. But the limitations of they have given the limitations of the Lidar is like the core limitation of the Lidar is like time taken for the data processing and cost effective and lacks in some environmental conditions. This paper reviews sensor technologies for autonomous vehicles with specific focuses on reducing sensor count to single digit sensor based system. The author examined how single camera can detect a road obstacle, including overtaking vehicles, pedestrians, and signboard bicycles and lane markers and road curvature. It mainly focuses on single camera object detection. The objective of this paper is like they have taken a single camera and they focus for the object detection instead of taking the multi-sensor systems. They have taken AI algorithms for the evaluation for the single camera and determining the optimal technique for the processing information for the single camera. When I talk about the methodology, they have taken the single camera instead of taking the multi sensors like lidar and radar and the sensor fusion of the both. They have tested the single camera for the object detection. They have taken the three different type of cameras, that is monocular vision, stereo vision, and classified camera for the autonomous driving applications. Analyze the different features of the three cameras and including the inverse perceptive mapping and neural network architectures in these both three cameras and reviewed using the CNN and RNN models and assess the performance metrics of the three different cameras by the accuracy percentages, processing times, and maximum detection distances. The limitations of this paper is like environmental factors like ambient light significantly affect the camera performance. Cameras have restricted viewing angles compared to the multi-sensors because in multi-sensor we have one-sided lidar and another side is radar. So both regions were covered by the two sensors, but in single camera we can only detect the 180 degrees only. When we use the 360 degrees camera, we can make it 360 degrees. And in complex objects like pedestrians, from the longer vision, it is hard to detect. And uh, for the longer distance, the accuracy also falls to low. And the conclusion of this paper is like single camera type offers a cost-effective alternative for the expensive multi-sensor array, and advanced algorithms and AI complex for the physical limitations of a single camera. And they have successful in performing the critical functions like lane detection and obstacle avoidance, but they have lagged in far object detections. This is the comparative analysis of the first four papers. Uh, this is the comparative analysis of the next four papers. Uh, when I talk about the base paper, this is my base paper. First, I have taken the research on comparison of lidar and camera in autonomous driving by paradigm. This paper mainly focuses on theoretical data instead of practical. They mainly the content is good in theoretical, and then I have gone through the comparative analysis of camera, lidar, and fusion based deep neural networks for the vehicle detection. In this paper, they have mainly focuses on real time comparison and like technical thing than the theoretical thing. So I need to fuse these both papers and taken as my base paper. Why I have chosen these papers is like that balance comparison in lidar and camera technologies. In some papers they have done they have mainly focuses on lidar, and in some paper they are only focused on camera. In some they have only focuses for the sensor fusion only. So for that purpose, they have chosen this fusion of these both papers. Mm, these papers mainly focus on perception layer improvements, which is crucial for the comparative analysis. I have framed my problem statement from the limitations of the base paper. That is current perception systems in self-driving cars like camera, lidar, and sensor fusion suffers from the crucial limitations like camera having limitations in low light conditions, poor performance in low light conditions, and lack in depth perception, and it prone to motion blur when it is in the far distances. Mm, In lidar system, it is cost high and weather sensitive, and it need to move. It can consume more power for the data pre-processing work. In sensor fusion, we need to fuse the both lidar and camera. It is having some advantages, but the limitations of this sensor fusion is like lidar need more power. For sensor fusion, it needs more power than the lidar, and it need more time for the data pre-processing than the both, and it is complex for the integration and synchronization issues, and increase in the cost of the system. This is my proposal solution, that is unified neuromorphic depth vision sensor. It is inspired from the brain. The unified neuromorphic depth vision sensor combines the event-based vision and real-time depth sensing in a single compact format, which offers the low latency, low power consumption, and robust performance in challenging driving conditions, eliminating the need of separate lidar, camera, and fusion systems. The unified neuromorphic depth vision sensor is advanced bio-inspired vision system that combines event-based and depth perception in a single device. It is designed for the high-speed, low-latency, and energy-efficient applications like autonomous vehicles and robotics. When I talk about the working principle of the unified neuromorphic depth vision sensor, mhm, it having two key principles, that is event-based vision. It uses a grid of asynchronous pixels that only responds to change of brightness, that is called events. Each pixel work independently responds, and when it detects a change in light intensity, this eliminates the need of all capturing all frames. This enables high temporal resolution, low power consumption, and high dynamic evolution. When I talk about the second part of the working, that is depth sensing mechanism. In this, it is having two stereo cameras which are similarly like human eyes. By comparing the timing and position of the events in the both views, it calculates the depth by using triangulation, and it is having spot single photon eventuate diodes. These are ultra sensing sensors that detect the individual photons. They measures the how long it travels from the light pulse after returning after hitting an object, that is using of time of light, which is similar technology used in lidar. Mm, then they will find the pursued depth according to this distance. Then we need to integrate this on chip event processor. Then it processes the stream of events in the real time and enables fast decision making with very low light latency. When I talk about the working event based pixel array, uh, in each pixel contains a photodiode logarithmic amplifier and comparator to detect the brightness changes. Signal synchronously emit the spikes events on for the brightness increases, off for the decreases. Then depth syncing mechanism, stereo comparison, two neuromorphic cameras with a known baseline distance compute the distance via the event based stereo mechanism that I have said before, that is using of the um, triangulation. They compare the positions of the events in the both views and find the depth. And by the hybrid reward circuitry combines the event-based data and the depth data and uses neuroformic processor for the real-time fusion. And the processing use and the passing unit they have used like Intel Lohi or brain chip processing for the events and the depth in parallel manner. They perform spike-based depth estimation. Uh, I will play a video for the working of these unified neuromorphic depth vision cameras, depth vision sensors.
Discover the unified neuromorphic depth vision sensor, crucial for self-driving cars. Watch as the sensor captures depth and vision data in real time. This technology enables cars to navigate complex urban landscapes safely. Intricate components include depth sensors and vision recognition tools. The integration of these sensors enhances vehicle intelligence and autonomy. As the urban landscape evolves, so do the capabilities of these sensors. The unified neuromorphic depth vision sensor represents the future of autonomous vehicles.
Uh, the main limitation of this unified neuromorphic sensor is like it is in the starting stage only. So it is having low data to present the working and construction. So I have present the AI video. And that also it is not mainly focused on working and construction. They, in spite of that, they have tell how to use and where to use. And this is the core performance metrics of the traditional camera, Lidar, and sensor fusion, and unified neuromorphic depth vision sensor. Um, the limitations of these three technologies will overcome by the UNDVS, that is motion blur, which struggles in the camera, but it overcomes in Lidar are affected by the camera in the sensor frame. But in the when I talk about the UNTVS, it eliminates the blur with the microsecond event response, and it overcome the very low latency event based processing, the low latency, and ultra low power saving using by the accurate pixels, depth accuracy with the high event based stereo or time of flight to overcome the depth accuracy, a dynamic range. It will perform the it will give the good accuracy in the dynamic range also and in low light also. When I talk about this environmental system level capabilities, the limitations of these three will be overcome by the UNDVS. That is performance in bright light. UNDVS handles direct sunlight without any overexposure. Performance in darkness. Functions in darkness using photosensitive technology. Weather robustness. It will works good in a fog, rain by using the event-based sensing. Cost and size. Uh, it is low cost, it is compactable, and it is in a single chip solution. No moving parts, no collaboration required. The key takeaways of the event device is like event device eliminate motion blur latency, which is crucial for the autonomous cars, drones, and robotics. Works in extreme light and in low light, and low power, low cost, no calibration issues. Better in adverse weather conditions. The conclusion of my case study is like instead of using the lidar camera and sensor vision of the lidar camera, which is high cost high compute which require high computation energy, high power. So in spite of these technologies, we can use unified neuromorphic depth vision sensor, which is faster response, use less power, works better in on-light conditions, and is more compact and cost effective. It is better for the self-driving cars. Uh, but the only limitation of this UN device is like it is in the developing stage only. But I am not. It is not come into the real-time application. These are my references. Uh, Instead of using the three technologies, we can use UNDES. That's the conclusion of my case study. Thank you.